All right, so today we're going to be talking about vertical circular motion, which we also call non-uniform circular motion. Okay? All the circular motion we've dealt with, including the rotating space stations, has all been uniform circular motion because the speed of the object didn't change. Okay? It was constant. Its velocity changed because its direction was changing, but its speed was constant. Now, we're going to look at vertical circles where the speed of the object actually changes as it moves around and around in the circle. So if I have an object moving in a vertical circle, okay, this is what it's going to look like. Now, are there points in the circle where it's going faster than others? Where's it going the fastest? Bottom. What's that? Yeah, so it's going fastest at the bottom because what's pulling it down? Gravity. But as it's moving upwards, gravity's pulling it down. It's slowing it down. Okay, so gravity now plays a factor in this motion. It doesn't play a factor, okay, here. Right? It doesn't play a factor here because the object doesn't move vertically. Right? So its inertia is enough that it won't move up or down. It just moves horizontally. Okay, so its speed doesn't change. Okay, but that's why in the lab, if you recall, I said make sure your circle doesn't look like this, because a few people were, their circle wasn't perfectly horizontal. Okay, and that means that you're now bringing gravity into the equation and having your speed change throughout the circle. Right, so in a vertical circle, the speed changes. Now what that means is that there's a certain speed I've got to travel at, or I drop. Yeah? Okay? How many people have seen the Simpsons movie? Where Homer tries to tackle the ball of death. Okay? He has to ride the motorcycle around the inside of the ball. Okay? And the first 3 times, yeah, it's scary at the top, and he hits the brakes and falls flat on his head. Okay? Like 3 times in a row. Right? And then Lisa tells him you have to speed up. Okay? And she's right. There's a minimum speed that you have to attain at the top of the circle if you're going to stay in the circle. You go that fast or faster, and you stay in the circle. Okay.
So when it's going like around vertically, is it like it does reach constant speed?
No. Its speed is constantly changing. Yeah. Okay. I mean, it's always, even in a uniform circle, its velocity is always changing because its direction is changing. It is always accelerating, just the magnitude doesn't change. Okay. Now, the magnitude and the direction change in a vertical circle. Does that make more sense? Okay, so if I go just fast enough to stay in this circle, okay, so I do actually stay in the vertical circle, how hard do you think the string is pulling at the top? Not at all. Exactly. Okay, if I go just fast enough to stay in this circle, effectively this thing becomes a projectile. Okay? And it's just traveling along a projectile arc at the top of the circle. How would a person doing that feel at that point? Zero gravity. Yeah, they'd feel weightless. In NASA's zero gravity trainer? Yeah, the vomit column. I'm going to show you a video of that today. Okay? Yes. Yes, you do. Okay, so what we'll see, guys, is how you can create a feeling of not true weightlessness, because to be truly weightless means there's no gravity. Okay, there is gravity, but it's apparent weightlessness. As long as I move in the right pattern at the right speed, I can create a feeling of weightlessness. Okay, even though I'm not actually weightless. Even Chris Hadfield and all the other astronauts on the International Space Station, they still have weight. They're actually only experiencing apparent weightlessness, because when you orbit the Earth, you're actually always falling. So you feel weightless. Okay? They're just going fast enough that they never fall closer to the Earth. Okay? The Earth is round. The Earth is round. Okay? In case there's any of you flat Earth crazy people, okay? The Earth is round. It is a sphere. Okay? And you can orbit it because it's not flat. Crazy. Okay? So if you're orbiting the Earth, then what you are actually is a projectile. Okay? Anything orbiting the Earth actually doesn't have to be powered. It just needs power to get into orbit. Once it's in orbit, it'll travel and orbit the Earth constantly because it's always falling towards the Earth but never getting any closer. Okay? So we'll talk about that later on when we talk about satellites, but today we're going to look at vertical circular motion, okay? The forces that contribute to it, obviously gravity is one, okay? And we're also going to look at this formula, okay? We've actually looked at it before. Centripetal force equals forces acting into the circle minus forces acting out of the circle. Okay? Now, that's not a new formula, because all that formula is this. Net force is the sum of all forces. Okay? I'm subtracting the forces acting out from the forces acting in. As long as I get a number there, then I have a net force into the circle, and the object travels in a circle. Everybody follow on that? Okay, so really all we're doing is calculating net force. Okay, so I'm going to show you here just a couple of quick videos on vertical circular motion before we get... Probably. All right, so if you're going to perform this loop-the-loop trick, like the rednecks we just saw, okay? When they go around the loop, you have to reach a certain minimum speed. If you don't, you fall out of the loop, and you always fall out of the loop at the worst spot, the top, and fall on your head. Okay? So obviously you don't want that. You have to attain a certain minimum speed in order to continue to travel through the loop. Okay? Now what we know is that our speed as we go through a loop like this is going to be at a minimum at the top and a maximum at the bottom. Okay? And then obviously somewhere in between on either side. Are we okay with that idea? Okay. If I'm going just fast enough here at the top of the circle, okay, what force is pulling me towards the center? Gravity. Okay? If I'm going just fast enough to stay in a circle, gravity pulls me towards the center, which means gravity is acting as a force. So if I'm going just fast enough to stay in the circle, Fc equals the forces in minus forces out. Well, there aren't any. There are no forces out in this situation. Okay? There's nothing trying to actively pull me straight out of the circle at that point. Now, if I'm going faster than the minimum speed, which the rednecks were doing after they hooked up to the truck, okay? Would there be additional forces?
Yes.
Okay, what additional force?
Friction.
Well, friction would be here too, but it doesn't contribute because it doesn't act in or out. Nope.
If you push them back onto the top.
Exactly. Normal force. Okay? Remember, my inertia, or I think that's what you meant, Gavin, when you said momentum. Okay? My inertia wants me to go this way. But the track prevents it. Which way does the track push? Down. Okay? That's the only direction the track can push at the very top. So, I would have gravity pushing into the middle, and I'd have some normal force pushing back into the middle. So, I go back to this formula, I say Fc equals forces in minus forces out. There still aren't any forces out, but now there's two forces acting in. Okay? Everybody all right with that? Okay. So, those are the two forces that could be present at the top of the circle. What forces might be present at the bottom? Gravity. Which way is gravity pulling? Right. It's pulling out of the circle. It's normal force. Which way is it pulling or pushing? Up. Okay, now, how is normal force at the bottom going to compare to normal force at the top? Remember, normal force is a reactive force. Here at the top, normal force is only reacting to how much your inertia causes you to push on the circle. Down here at the bottom, you have your inertia causing you to push on the circle, and you have your force of gravity. So where do you feel the heaviest? At the bottom. Yeah. Okay. We have another name for Fn, and you'll probably want to write this down. Okay. We oftentimes, especially in this unit, refer to normal force as apparent weight. Okay? Because it's the weight we feel. Under normal circumstances, my apparent weight and my real weight are equal, like right now. Okay? My apparent weight that I feel against my feet is equal to my normal weight. But if I start putting myself in a circle and start moving really fast, I don't just have the force of gravity, I've also got my inertia pushing on the circle and the circle pushing back, causing me to feel even heavier. Right? Everybody okay with that? Okay. So bottom is where you feel heaviest. Now, what if I'm going on the outside of the circle? What if I'm out here? Now what forces are acting on it? Gravity. Gravity's pulling. Which way is normal force pushing? Out. Okay, so remember, we have our formula here. Forces in minus forces out. Okay, for this situation, that's Fn minus Fg. Okay, because Fn is in, Fg is out. Here, Fc equals force of gravity minus normal force. Okay, always forces in minus forces out. Now, if I go fast enough over the top of this circle, what will I do? I'll drive off of it. Exactly. I'll leave the circle if I go fast enough. Okay? You've probably experienced it before. If you go over like kind of the top of a sharp hill in a car, you feel like your stomach and everything kind of moves up into your throat. Okay? You feel a little lighter than normal. That's what you're doing. When you go over the top of a vertical circle, okay, you're causing your apparent weight to decrease because you're trying to become a projectile. Okay? If you go fast enough, you actually become a projectile. And if you leave the ground, are you pushing on it anymore? And then the ground can't push back on me, and my apparent weight becomes 0. I feel apparently weightless. Okay? This is how the zero gravity trainer works. They take a 747, they have all the seats and stuff taken out of it, okay? And they go into the sky and they fly in a pattern like this. Right? When they're down at the bottom of the circle, everybody feels really heavy. Okay? But as they're going over the top of the circle, everybody feels weightlessness for about 30 seconds. Right? This is how they shoot a lot of science fiction movies, okay? Like The Martian and Apollo 13 and movies like that. Okay? The zero gravity shots are actually filmed in the zero gravity trainer. Okay? 30 seconds at a time. Right? So that they actually get the real look of weightlessness. Because it's basically impossible to make weightlessness look real with cables. Right? It just never looks right. But if you do it this way, it looks really realistic. All right, so we're going to have a look kind of at that. Now, like we said, bottom of the circle, okay, you're going to feel really heavy. Top of the circle on the inside, okay, if you're going fast enough, you'll feel a little heavier. Okay, but if you're going just fast enough to stay in the circle, you'd feel weightless. If you're going over the top fast enough, you'd feel weightless. Okay? If you're going over the top but not fast enough to lose contact with it, you're only going to feel, partial. You feel lighter than normal. Your apparent weight will be less than your normal weight. Okay? And so that's true for any vertical circle. Okay? Like even the speed bump out here, okay, on the road leaving the school, okay, that's a vertical circle. Right? If you were, you're not going to do this. If you were to go over that really fast, would you jump it? Don't. Okay? The first year we were in this school, we had a kid who did it, and he destroyed his car. Okay? Because he had like 4 friends in it. It was like a hatchback. And he hit that really fast, and then when they came down, it bottomed out. Car made this awful sound and then died forever. Destroyed. Okay? Luckily, nobody was hurt. Got pretty. He ended up getting suspended. So, not safe. Don't do that. But that's what vertical circular motion. That's how it would apply. Okay, to that situation. All right. So I'm going to show you a couple of videos here of applications of this. Okay, where we kind of see the uses for this. When I talk about high G training, what I mean is fighter pilots have to be trained so that when they make turns in an aircraft, they don't lose consciousness, because that can happen. Okay? If they take a tight turn in an aircraft going at a high rate of speed, they'll experience G forces. Some of you have heard that term before. Okay, so G forces are what you feel if your normal force or your apparent weight is different than your actual weight. Okay? The human body can actually endure very high g-forces as long as they're not long duration. Okay? So we could endure even something as much as like 20 Gs, as long as we didn't have to endure it for more than about 5 seconds or so. Okay? If we endure even small amounts of g-force for extended periods, it can be difficult for our body to adjust to that. Because what happens is, not only do we feel heavier, everything in our body is kind of heavier, including our blood. So if I'm taking a high G turn, okay, the blood that's supposed to be pumped to my head could be as much as 7 times heavier than normal. My heart's not designed to pump my blood when it's 7 times heavier than normal. It's designed to pump it when it's normal. So if I endure that G-force for any length of time, the blood drains away from my head. Okay? I start to get tunnel vision, see spots, and eventually black out. Right? This may happen to you next week. Okay? It does occasionally happen on the Mindbender. Okay? Because the Mindbender is a vertical circle. Okay? So it is possible to black out in the loops on the Mindbender if you're especially sensitive to it. Okay? Or if you've ridden it a bunch of times in a row. Okay? It can happen. And it's kind of funny because you hear people like they're screaming and all of a sudden they're really quiet. And then when you see them on the other parts of the roller coaster, and he's bobbing all over the place because they're out. Okay? But it can happen. So if I'm flying a fighter aircraft and I'm at the bottom of this circle, remember that gravity is trying to pull me and my blood away from my head. My inertia is trying to send my blood that way. Either way, neither one of those directions is towards my head. Okay? And so as a result, the blood is just pulled away from my head. My heart can't pump it there. Okay? My brain becomes starved for oxygen. Okay? I'll show you what that looks like. Video here of a guy. Okay, so what we have as we're going around the circle is not only a change in speed, but we have a change in speed because of a change in not only the magnitude of the forces involved, but the direction of the forces involved. So when we're on the bottom of the circle, we feel heaviest because normal force is very large. It's counteracting gravity and inertia. Okay? On the sides of the circle, gravity is perpendicular, plays no part at all. Okay? It's not in or out of the circle, it's perpendicular. Okay? So we only have the centripetal force, okay, pushing inwards. At the top of the circle, if we're on the inside of the circle, okay, then we have normal force pushing down, gravity pulling down. Okay? If we're going just fast enough to stay in the circle, this force is 0, and we feel weightless. Okay? And if we're on the top of the circle, gravity pulls down and normal force pushes up. But it only pushes up if we're not going too fast. We go faster than we need to, then we leave the circle, okay, and we feel weightless. Yes. Okay? Everybody kind of follow that? All right. So this is what we do to give a feeling of apparent weightlessness, is to fly over the top of a vertical circle, okay, in order to produce that feeling. Now, this music group called OK Go, has anyone heard of that? Mm-hmm. They have like the coolest music videos because they're like really physics oriented and they can think up the most amazing things to try with their videos. So what they did is they filmed one of their music videos inside the zero gravity train. Right? So it actually looks really cool, okay, as it plays through. So you can actually see, if you watch carefully, you can see when they're going over the top of a loop and when they're headed towards the bottom. They actually tried to make the whole video so that it was only all weightless, but you can kind of see as the weight shifts if you watch things that are in the cabin with them. Right? So I'll show you that here. Okay, so now we've seen a few applications of that. Yeah. Okay. So here's what we want to look at now. Okay, as you go around, okay, anywhere where you're going in the circle, obviously the formula for FC changes because the forces acting are changing. Okay, at some points in the circle, it's going to be normal force minus gravity. Other points, it's going to be gravity minus normal force. Some points are going to be added together. Okay, but what is consistent is this. That is that the centripetal force is always the net force. Forces in minus forces out. So all we have to do is make sure that we can identify the forces at any point in the circle and subtract them in order to get FC. Right? So what that might mean is you could have problems that ask you, given a radius, a circle of this radius, okay, what speed do you have to travel at in order to stay in the circle? Or you're going over the top of a vertical circle, what's your apparent weight if you're going this fast? Okay, and you'd be solving for other things within the equation. So we'll look at a few examples here. Apparently that's a real thing too, where you drive your car. You guys have these like Hot Wheels things as a kid? So you can actually drive a real car after one of those. Okay, now, obviously roller coasters use this same idea. Okay, they use the same idea of using a vertical circle to create g-forces, because g-forces give you the illusion of speed. They also give you the illusion of danger. Okay, because you feel heavier, you feel thrown around, you feel unstable. Okay, so obviously they utilize things like having a high rate of speed or having tight loops. Now, I mean, the Mindbender is an older roller coaster. It was built in the 80s. Incidentally, it did actually go off the tracks and kill some people at one point. But they won't do that now. The reason for that actually was the whole thing was designed and fabricated in Europe, and then all the parts were shipped over to Edmonton, and it was assembled there without the engineers who designed and fabricated it. Now, in the blueprints, it says very clearly the maximum length of a train on the roller coaster is 3 cars. They built trains 5 cars and started it going around. Well, when you have these really tight loops and tight corners, there's a lot of force on the back of the train that isn't there on the front, and it leads to a whipping action that eventually loosened the parts of the car enough that they were able to lose contact and actually come off the track. And then, of course, when one comes off, it pulls the others with it. Okay, so you'll notice that when you ride. If you ride, like when you ride the Mindbender, ride in the front and ride in the back. Okay, it's different. You feel thrown around a lot more in the back car than you do in the front car. Now, hopefully, because they've had this about 5 times, this is our 46th trip.
I thought
46. Mr. Dickey's done this. This is his 46th trip. Okay, so about 5 or 6 of those times, they've had this one train where the back cart faces backwards. It's a whole new ride, okay? Because if you're riding it and you're facing forward, you see everything coming. If you're riding that one that faces backwards, it's all blind. You don't see anything coming. It's a whole new ride. Okay? But you do get thrown around a bit on that one. All right, so I'm going to show you here a couple of kind of the other roller coasters. They have these loops on them. Okay? I'm going to show you, well, Boomerang doesn't work anymore, but Griffin hopefully will still work. So I'll show you what that one looks like, okay, and how they use like Immelmans. Immelmans are these loops. The tighter the loop is, the greater the g-forces. Now, the Mindbender, even though it's an old roller coaster, has some of the tightest loops in the world because it's indoors. So by the fact that it has to be indoors, it can't be as tall. Okay? If you've ridden that one at Callaway Park, okay, the Immelmans, the loops are way bigger. Okay? So you don't feel as crushed and stuff on that one as you do on the Mindbender. Because the Mindbender, when it goes through those loops, is going over 80 kilometers an hour. Okay? And it's going through a loop that's only about 7 meters in radius. Okay, so it's really tight. So we're going to try this question here. We want to calculate the minimum speed. So think back to when Homer was doing the ball jet. Okay? The minimum speed to stay inside the loop. So what we have to remember here is that if I'm going just fast enough at this point right here to stay in the loop, what force is pulling me in? Gravity. All right, but since I'm going just fast enough to stay in the loop, do I push on the track at all? And if I don't push on the track doesn't push back. So I only have this one force acting on me. So Fc, which normally equals forces in minus forces out for a vertical circle, there are no forces out, and there's only one force in. Okay, so what I end up with is that Fc equals Fg, mv squared over r equals m times g. Have we had that come up a bunch of times already? Yeah, okay, it comes up all the time. All right, so we're looking for the minimum speed. So we're solving for v. So I'm going to multiply both sides by r. M is going to cancel, and I'm going to square root. We've had that formula as well before, right? V is the square root of curve. Okay, so that's going to be 9.81 times 9. Okay, so we'll have the square root of 9.81 times 9. So the minimum speed for that roller coaster is 9.4 meters per second. Right? If it went only 9.4 meters per second going around the top of that loop, everyone on it would feel weightless. You would never build a roller coaster that flirts with that number. Okay? It's dangerous. If you have it go just fast enough to stay in the circle, it is possible that if there was anything wrong on a particular day or conditions changed at all, it might not make it all the way up, and then it would go backwards. Okay, through the thing, right? And then not be recoverable. You would have to like pick the thing off the track and take it back to the beginning with a crane, right? Because roller coasters rely on the initial mechanical energy to get them all the way around the whole cycle. Okay? If they don't have that, if they stop anywhere in between, okay, then they won't make it all the way through. The reason we got all the way through when we got stopped was we got stopped at the very top, at the highest point. So we had tons of mechanical energy to get through everything, thankfully. So that was like, nobody screamed on it. It was like the quietest Mindbender ride ever, because everyone was too scared to scream. And they never told us why the cart stopped. It just, let go, and then off we went. It would be nice somebody come over the speaker and say, no, it's just a glitch, no worries, everything's fine. No, they just let it go.
Sat there for 5 minutes.
Sat there for 5 minutes wondering what the heck is wrong, am I going to die, and then it just starts going. Wasn't fun. Okay.
That doesn't work.
Now, like we said here, so this is what we just did. The minimum speed occurs when you go just fast enough to stay in the loop and only gravity acts on it. Okay? All right, so when we did that calculation, we got 9.4 meters per second. All right, so we got a couple other example problems here that we'll probably walk through, and then tomorrow we'll spend some time looking at vertical circular motion stuff, and then we'll be almost done the first half of this unit. And you'll know everything you need to know to answer all the questions for West Edmonton Mall. Don't pack up, we're not done yet.
What?
Yeah, still got 3 minutes.
No.
Great. I want you guys to try this one right here. We have a 700 kilogram roller coaster full of people. Okay? The loop is 50 meters in diameter. Is that a trick?
Yes.
What do you need?
Radius.
Okay. I want you to calculate the minimum speed of the roller coaster. In order to stay in that loop, it is exactly the same calculation I just performed, so we'll see how well you were listening.